Dawson is a master's student here at Laurentian University under the supervision of Dr. Katie Goggins and Dr. Marcus Tumusk. He also did his undergrad at Laurentian in the mechanical engineering program, and he's doing some pretty innovative stuff. So I'll let you take it away.
Thank you, Dr. Darman. So good morning, everyone. Thanks for coming. Today I'll be talking about my master's research project where I'm developing an instrumented insole to measure foot transmitted vibration. I'm co-supervised by Dr. Katie Goggins and Dr. Marcus Tamask. So just for a quick outline, I'll be talking about some of the gaps in the research on foot transmitted vibration, the current methods for determining vibration exposure, the insole design, and as well as the results from some preliminary testing. So exposure to foot transmitted vibration has possible health risks from chronic exposure. Like Dr. Aaron Thompson mentioned, very in-depth. Foot transmitted vibration exposure can also affect the feet like it does the hands. So you get that neurological with the numbness and tingling. There can be a reduced sense of touch and temperature, as well as temperature sensitivity in more colder climates. There's also vascular symptoms affecting the blood vessels in the feet. These symptoms are more noticeable and referred to as vibration-induced white foot because the toes blanch or go white due to poor circulation, especially in cold weather. And the last possible is bone and joint damage due to the excessive physical stress or strain of the joints when exposed to vibration. Foot-transmitted vibration can also fatigue lower limb and postural muscles after prolonged exposure. In 2022 in Canada, according to the Association of Workers' Compensation Board of Canada, there was 348,747 accepted lost time claims. Most of these lost time injuries were from a traumatic injury disorder, with the second lost time injuries occurring due to systemic diseases and disorders. Then there's a category called symptoms, signs, and ill-defined conditions, and other for other diseases, conditions, and disorders. So if we assume a traumatic injury to be an instantaneous exposure to a hazard, then the symptoms we just defined in the previous slide could fall under the next three biggest categories of lost time injuries. This makes it difficult to isolate the effects of whole body, hand transmitted, or foot transmitted vibration. We also have to keep in mind that these numbers are from accepted claims only, and not all accepted claims, or not all claims are accepted, meaning these numbers are probably underestimating lost time injuries in Canada. So in 2009, the Australian Safety and Compensation Council, now WorkSafe Australia, surveyed 4,500 workers in agriculture, mining, transport, construction, manufacturing, health, and community services to determine whether they're exposed to vibration. Of the 4,500 participants, 1,358 reported that they experienced vibration exposure at work. So 43% of those workers said they're exposed to hand arm only, 38% said they were exposed to whole body vibration only, and 17% said they were exposed to both. So you can see how foot transmitted vibration has not been differentiated, and we have to guess whether the worker was in a standing or seated position based on the type of equipment they were running for both the whole body vibration and then the hand, arm, and whole body. So this study completed by Leduc and colleagues in 2011 measured vibration exposure of workers in the mining industry. So exposure of two locomotive, a bolter, a jumbo drill, and multiple raised platform operators, both wood and metal, were recorded along with the dominant frequency of their work. And this comes up later when we talk about some of the key things we're looking into. So the daily exposure was calculated according to the ISO guidelines that Dr. Thompson talked about. So there's three different categories there to differentiate the risk of developing musculoskeletal disorders. For the locomotive, bolter, and jumbo operators, ISO standards predicted a low risk of developing musculoskeletal disorders, but both types of raised platform operators are within or above the health guidance caution zone, where the risk of developing musculoskeletal disorders becomes high or moderate. Dominant frequency of the vibration is also important to consider, as certain frequencies may further increase the risk of developing musculoskeletal disorders if the frequency is within the range of resonant frequency of certain parts of the body. And so this figure shows all the participants of a study Dr. Goggins and her colleagues completed in 2016, which also evaluated exposure to vibration of locomotive, crusher, bolter and jumbo drill operators. And so one of the major findings of the study was that only 2 of the operators exceeded the ISO health guidance caution zones. One participant exceeded the whole body health guidance caution zone for vibration exposure while bolting. The other participant, so that's the first person in green and the first person in orange, operated both the bolter and jumbo drill, and they exceeded both ISO health guidance caution zones in the hands while bolting and whole body while operating the jumbo drill. Additionally, they also surveyed pain or discomfort in the body, and multiple operators reported that they experienced severe or very, very severe musculoskeletal discomfort. And so that's marked by a red box in either the upper or lower area of the body that they experienced the pain in. So this may be an indicator of increased risk of developing musculoskeletal disorders. And finally, multiple participants were diagnosed with either white hand, which is outlined by the gray box on the hands, or white foot, outlined by the gray box on the feet, or both of those, white hand and white foot, even though their exposure levels were under the ISO guidelines for increased risk of musculoskeletal disorders. So we've covered some of the results from the measurements, but what are the methods of taking these measurements, either in a field or a lab? So in the first column, we have a laser Doppler vibrometer, generally shortened to LEV, which uses lasers as the measuring system. So this option can measure multiple locations at the same time with very high accuracy. It does this by measuring the wavelength and the shift of the wavelength due to the vibration of the laser reflected off the surface it measures, which is called the Doppler effect. Some of the main drawbacks of using an LDV is that it needs to stay completely stationary, so it has to be off the platform or surface you're measuring, so it can achieve accurate results. And it could also only measure one axis at a time, and you have to limit the tilt on the head of the sensor. That's say pretty close to vertical, and then you also need to apply a correction factor if you're off that vertical. So the second column has the characteristics of piezoelectric accelerometers. These are generally mounted to the platform or surface we're taking the measurements on. So these also allow for field measurements and not solely lab studies. So these contain a small quartz crystal and 2 common setups. So there's compression style where the crystal gets compressed, or shear style where it's placed in like a beam configuration and the loading from that creates a small charge that we record. And so these style of accelerometers can measure in 3 axes and not only one axis like the laser Doppler vibrometer. And then finally, we have a MEMS accelerometer. Like the piezoelectric accelerometer, this device is mountable to a surface or platform. It can measure multiple axes at the same time and may be also used in the field. MEMS accelerometers have sets of capacitance plates. So one set's fixed and the other one can move. And then when you have that vibration, it changes the distance in between the 2 plates, and that's how you record your vibration. And so we can use all 3 types of these devices to measure vibration and evaluate both the health risk and how to design different products that we can use, like seats and gloves. So there are standards to evaluate the health risks for both whole body vibration and hand transmitted vibration, as well as standards for the effectiveness of suspension seats and for gloves. There are currently no standards focused specifically on the feet for either the health risk or boots and insole designs. While we use the whole body vibration standard for analysis right now, like Flavia said, it doesn't focus specifically on the feet. It only says it's applicable to the feet. So a common area all these methods of measuring the devices are used is on the hands. So LDVs have been used to measure the surface of the hand, piezoelectric accelerometers to measure the response of the arm, so that's into the forearm and into the bicep. And then the MEMS we can also use to measure vibration at the contact point, so of the palm when we grip a tool. And then in the field, it is common to measure tools specifically. In this case, a fully rigid adapter is required to accurately measure the vibration of the tool at the contact point. Recently, instrumented gloves have also been used to track the person and not the tool. So this allows for a better estimation of a day's exposure, especially if a person moves around from machine to machine. And when we measure vibration exposure in the foot, we have two methods for lab measurements. So the first is measuring the platform marked by the red square on the left. And this is generally a piezoelectric accelerometer. And the second being reflective markers for use with the laser Doppler vibrometer. And that's placed on the top of the foot, or a small MEMS accelerometer is taped to the foot. And then here we have an example of a field measurement on the bolter. Currently, the platform is measured with piezoelectric accelerometers, but this limits our full understanding of the effect of foot transmitted vibration because we have those mats, we have boots, and stuff like that. And we see that better in this slide here, where you can see just how many layers there are that could dampen vibration or even amplify vibration, but we have really no solid understanding of it at this moment. And so changing posture and contact conditions in the hand has also been studied by multiple researchers to better understand hand transmitted vibration. The change in posture and contact conditions can not only change the resonance in the hand, but the transmissibility of vibration through the hand. The bottom figures from a study completed by Consonetti and Griffin, where contact conditions were evaluated, is comparable to shifting the center of pressure in the feet. So that's like changing posture. And then Flavia and her colleagues compared the responses of the hand and foot to vibration at 12 anatomical locations to further link hand transmitted vibration and foot transmitted vibration evaluation methods. Like I said before, the current standards group the feet under whole body vibration standards, but her research showed that the standards for evaluating hand transmitted vibration may be better suited for evaluating foot transmitted vibration. And then one of the best studies on foot transmitted vibrations was completed by Dr. Goggins and her colleagues, where they used the laser Doppler vibrometer to measure the transmissibility of the foot. They used reflective tape to mark the locations for the laser. So the figure on the left shows the locations on each of the toes along with the lateral, so that's the outside, and the medial, which is the inside portions of the midfoot, known as the metatarsal. And the middle figure shows the locations on the medial and lateral sides of the ankle, along with the location they measured on the foot. So the figure on the right shows each location from above. The T's mark each toe, with T1 being the big toe. The P's mark each joint in the toe, with P1 being the nail bed of the first toe. M's indicate the medial side of the foot, along with L's indicating the lateral side, and H1 marking the heel. So this graph demonstrates the transmissibility results from their measurements. So starting with T1P3, the horizontal axis shows the frequency ranging from 10 to 200 hertz, with the vertical axis being the transmissibility. So when the foot's transmissibility is 1, the amplitude of vibration coming into the foot is the same coming out of the foot. Where we really want to focus is the range where the transmissibility is above 1. And so anything above that line is known as resonance, where the input vibration excites the foot, and the result is actually amplified vibration coming out of the top of the foot. So as shown by the red box, from 40 to 145 hertz, Dr. Goggins and her colleagues measured the transmissibility of greater than 1, with the peak at 75 hertz. So this range of frequencies all indicates resonance in the toes, where the risk of damage to the foot due to vibration is increased. Then comparing the results of the toes to the heel, we can see that the frequency ranges where they measured resonance in the foot varies greatly between the toes and the heel. The heel of the foot was shown to resonate at 10 to 35 hertz, and this shows that multiple measurements are needed to accurately measure the response of the foot when exposed to foot transmitted vibration. And especially at the heel, as the resonance range is the same as the dominant frequency of many operating equipment in mining, like the raise drilling and jumbo drills. And so this is an example of an insole built by Mazzaroli and colleagues in 2021 to measure vibration exposure inside of a shoe. They used a MEMS accelerometer along with a force-sensitive resistor to measure exposure to vibration at the heels and toe, along with wireless charging and Bluetooth data transfer to create a wireless insole. So while this didn't measure at ISO standards, it provides a background to continue on to the next step in developing an insole. So the first thing to improve upon is the accelerometer they used. So this was a great starting point to go off of because it shows what you can do. So by using a better MEMS accelerometer, we can up the sampling rate so we can sample at those ISO standards. Additionally, using Bluetooth data transfer to keep their insole wireless, they lost some data. So to prevent that, we've used a wired setup. So this is more for a lab-based right now, but it will help to not lose that data. And then finally, unfortunately, the research was not continued and the company in control of the software went out of business. So we can't compare their previous insole to what we have currently right now built. And so this is a result of that background knowledge, along with using different components. So by changing to a wired setup, we can sample at the ISO standards so that we have comparable data to use with the hand transmitted vibration ISO standards. So using a 3D printed housing to hold a MEMS accelerometer, as you can see on the right, both those get glued into a spot that we've carved out in the insole to hold everything in the insole itself. And then all the communication and power wires come out of the heel and we'll tuck up the backs or side of the boot, depending on what's comfortable, and then off to a data acquisition card hooked up to our computers. So the first few tests to validate the insole were completed on all three axes, the X, Y, and Z direction, and compared to a calibrated piezoelectric accelerometer that was mounted on our rotopod, so that we can compare the data and make sure everything's working in the insole. So this axis shows this slide shows the overlapping graphs for the axis of interest. So in this case, the X, which is the front to back vibration of both the insole and the piezoelectric. So the blue graph is the insole and the orange is the calibrated piezoelectric mounted to the rotopod's platforms. The errors are calculated based on the root mean square average of the vibration and normalized to the calibrated accelerometer. For this test, the X-axis performed very well with under 1.5% error for both the toe and the heel compared to the movement of the platform. So due to the geometry of the rotopod, we do get some unwanted motion in the Z and Y and Z directions, which increases the error. And so the second test was on the Y-axis, so that's side-to-side vibration, with the blue graph again being the insole and the orange being the rotopod's platform. And so this test had less than 2% error for the axis of interest, with large errors again due to the geometry. And finally, the final test is the Z-axis or the vertical axis, so that's up and down vibration, where again, the blue is the insole and the orange is the floor of the platform. And so in this test, the error for the Z-axis was 1% or less, again, with error due to that geometry of the rotopod. And so here we can kind of see what that rotopod is. So it can't do purely one axis movement, just because of the way the legs go around to move that platform. We do see some X, Y, and Z, even though you're trying to do a single axis. So overall, a few sources of potential error have been identified. So the first, again, being that geometry of the rotopod. You can't accomplish purely single axis motion. So the next is finding a more secure method of mounting the insole to the platform. Due to the vibration, you have to completely rigidly mount it. And then finally, I used an impact hammer to align the signals at the start, but it proved to be unneeded as the start of the path for testing these insoles has a big spike in acceleration that we can use to line up our analysis. And so the impact of creating a newer version of an instrumented insole is the ability to use this method as a way of aiding design and vibration damping insoles by allowing for transmissibility measurements to be taken through the range of frequencies of both the resonance of the foot and of operating machinery. So similar to how vibration dampening gloves are evaluated along with suspension seats, we can also use this as a way to test boots and insoles, where we can actually mount the accelerometers used in the evaluation into the boot as well as on the platform. So this can create a new method for evaluating foot transmitted vibration both in the field and in the lab. Thank you very much for your time. Hope we're not too far over schedule now.
Sorry, I'm slow on clicking on the video. We are not. We have 3 minutes for questions, and there are 2 questions in the Q&A box. But first, let me say, great talk, Dawson. Very cool study. The first question is, what kind of bolter? I think referring to the introduction there when you were talking about the bolter measurements.
Yeah, so that was a McLean bolter. So we were able to put our accelerometers under kind of the working area where the operator would stand. So that's near the controls and by the boom head.
Okay, thank you. The second question is, do you believe that cold environmental temperatures can affect the test results?
So yes and no. Within a range of certain temperatures, the accelerometers will kind of stay linear in their performance, so it doesn't get affected too much when you're within like normal temperatures, so like from 0 degrees to 30 degrees. Once you start to go colder and hotter, it does affect it, but there is information from the suppliers on how to kind of track that change. So we can see just how much the accelerometers are affected due to different temperatures.
Okay. And I guess, does that translate to like anti-vibration, like footwear or handwear? Like, does cold temperature affect their ability?
I have a limited knowledge on that. Coming from a material side of things, I would say probably, like, as we all know, as you get colder, like plastic, for example, cold plastic breaks a lot easier than warm plastic. So my guess would be there
Mhm.
is something there. I can't say for sure.